All right, welcome everyone to the SIG Scalability intro. A few words about the speakers. My name is Matt. I'm a software engineer working at Google. I work on Google Container Engine, and I am SIG Scalability chair. Wojciech, who couldn't be here today, unfortunately, also works with me at Google, and he is our SIG Scalability TL. He should be during the Q&A session, so you can ask him all those difficult questions that I'm not able to answer. All right, so TLDR about SIG Scalability. What do we do? First of all, we define what is Kubernetes scalability. You will see in a moment that it's not an easy thing actually to define. And we also define what are the goals for the scalability. We protect from scalability regressions, mostly by maintaining scalability and performance test frameworks, and based on that, CI/CD tests. Other than that, we detect scalability bottlenecks and then drive performance improvements to get rid of them. Last but not least, we keep Kubernetes scalable by coaching and consulting Kubernetes community about scalability. And one important thing, please do not confuse us with SIG auto scaling. We share part of the name, scaling, but other than that, these are two completely different SIGs. All right, so now let's try seeing why defining Kubernetes scalability is not an easy task. So if you ask an average Kubernetes user, what do you want in terms of scalability? The obvious answer is scalable clusters. But when you ask what does it really mean, then usually people don't know what to say. And that's understandable because scalability is not an easy thing. Luckily, it's not that we are inventing a wheel here. Scalability is a known and really old concept in computer science. So we can take a look, for example, how Wikipedia defines scalability. So Wikipedia says that scalability is the property of the system to handle a growing amount of work by adding resources to the system. And actually, that's a very accurate definition, right? That's what we expect from scalable systems, that we can add more resources and then handle basically more load, more work. In fact, this is only theory. This is only theory, and it is only like ideal situation, and no real system actually has this property of scalability defined this way. Why? Because in any system, if you keep adding resources, you cannot add them indefinitely. Eventually, you will hit some bottleneck and things will start breaking. Eventually, you hit, for example, some log contention or you will hit some database contention or network issues, and you won't be able to add more resources to the system. And this is exactly the same about Kubernetes scalability. So in fact, the scalability and our everyday work in SIG Scalability is about discovering performance limits of a system and driving improvements to push these limits. This is much more accurate definition. All right, so there is also very often misconception about scalability. People believe that Kubernetes scalability is only about number of nodes in the cluster. On the left side of the slide, you can see some history of how many nodes we supported in certain Kubernetes releases. And we can say, okay, so as of now, we support 5,000 nodes. These are all these resources that we can add to the system. And as we said, we cannot add more because things will start breaking. And basically, that's all, right? That's end of the story. We can go home, end of presentation. In fact, it's not end of the story, it's just the beginning. And we need to analyze scalability, Kubernetes scalability in many more dimensions. And by many more, I mean hundreds, if not thousands. Nodes, number of nodes in the cluster, it's just one of the dimensions. It's a very important one, but just one of the dimensions. Other examples are namespaces, number of secrets, number of services, size of secrets, or config maps, number of backends per service. Then some virtual dimensions like pod churn, or like some other example of dimensions that touch to other dimensions like number of pods per node, and many more. And this is why scalability is difficult and hard, especially Kubernetes scalability. We need to analyze this multi-dimensional space, and to make things even worse, those dimensions, they interact with each other. So, for example, the number of namespaces a number of pods, there is a dependence between them. If you create too many pods and you have only one namespace, most likely you will run into some issues. Luckily, there is something that we call scalability envelope, is a subspace here, and is a safe zone. It means if you are within this scalability envelope, your cluster is happy. So our task as SIG Scalability is to make sure we are aware where exactly this safe zone is, this scalability envelope, and we basically provide this information to the users so they know how much they can scale their clusters. All right, so we more or less know the top-level overview of the scalability definition. Let's dig a bit more deeper into that and see how we can formalize this definition. All right, so as you can imagine, because of this multi-dimensional property of scalability, then defining and precisely computing this scalability envelope is basically impossible. We have too many dimensions and too many values those dimensions can take. Basically, it grows exponentially. It's not possible to test all configurations. Luckily, we don't have to do that. We don't have to provide a very strict mathematical definition of this scalability envelope. We can approximate it by a set of limits, and usually this is even better for the user because it's easy to understand the shape of this envelope when it's approximated by a set of limits. So what we say is that as long as your cluster will stay below 5,000 nodes, number of pods in the cluster will be less than 30 times number of nodes, you will have less than 10,000 services, you will have less than 20 or 250 backends per service, and etc., then your cluster should be okay. It should work fine. All right, but what does it mean that your cluster will work fine, is happy or scales? We also need to be a bit more precise here, especially if we want to have a framework where we can experiment and try pushing some limits. If we push one limit, we need to still be able to say whether a cluster is okay or not, right? If cluster goes down, that's an easy case. Obviously, cluster, it means it doesn't scale. But if it didn't go down, basically just maybe some, we notice some performance degradation by 10%. Is it still happy? Hard to say, right? That's why we need more precise definitions. And again, luckily, we are not inventing a rule. We can base it on a concept that work pretty well in computer science. So SLI, service level indicator, and SLO, service level objective. You can think of SLI as a metric, and SLO is this metric plus some threshold. So for example, API call latency, SLI, and SLO is that API call latency is less than 1 second. The SLOs that we have in scalability are listed here. You can read more at the link, the bottom of the slide. So the most important one is API call latency. We also have pod startup latency. We have a bunch of network-related SLOs like network programming or network latency or DNS-related latencies. All right, so that brings us to this definition. We can formally say, what does it mean that cluster scales? Cluster scales if all scalability SLOs are satisfied. And to put everything together, now we have this framework. We promise kind of framework. So if you promise to correctly configure your cluster and then stay within the scalability limits, then we promise that all scalability SLOs will be satisfied, meaning your cluster will scale, will be okay. Okay, and now based on this framework, we are running scalability tests. But before we describe scalability tests, in general, before you run scalability tests, you need infrastructure for that. And this is big part of our daily basis work to maintain and own all these scalability test frameworks and tools. The most important one is cluster loader 2. Single sentence description is cluster loader 2 is a bring your own YAML cluster load test tool. The motivation to create cluster loader 2 was that before our tests were written in Golang in an imperative way. So basically we needed to code all these operations for create deployment, then create config maps, then scale deployment up, scale deployment down, create daemons, and etc., etc. And once it reached certain scale or complexity, that has reached certain complexity, it became really hard to maintain and really hard to actually extend the test. So we had this idea that load testing could be much easier. And ideally, you would just want to declaratively provide a states the cluster should be in, and then something should bring cluster to those states. And that's what the cluster loader does. So basically, an input to cluster loader is a YAML file with a test, and test can be set of states. So for example, one state can be, okay, I want to have cluster with 30 pods per node, 10,000 services, some configs maps, some secrets, and cluster loader will bring cluster to that state. And then I have state 2 in the test, so I want to transition from state 1 to state 2, where state 2, for example, is 20 pods per node, but some extra daemon sets and stateful sets. And cluster loader will do that. And during whole test, cluster loader measures the scalability SLOs and checks whether they are satisfied. So basically implements the framework we have, pushing to the limits and then checking whether all scalability SLOs are satisfied. In addition, cluster loader provides extra observability of the cluster for debugging purposes. This is really important if something stops working, because in general, debugging scalability is not easy. So we need all those tools like dashboards, graphs, metrics, profiles, and cluster loader provides everything. In addition, it provides a bunch of extra features. We don't have time to describe all of them, but if you are interested, then there is a link at the bottom of this slide where you can learn more about cluster loader. Another important tool that we have is KubeMark. TLDR about KubeMark is a cluster simulation tool created to make scalability tests cheaper. And as you can imagine, to run like 5,000 node end-to-end test, you need at least 5,000 VMs for the nodes, then some VMs for the master, and then such test can take like the fully load cluster to certain pod density. It takes a long time. It can take hours, even more than 10 hours. So in general, such test is really expensive. And we created KubeMark to make those tests cheaper, so we can execute. So we could execute them more often. The idea behind KubeMark is that when we are testing scalability of Kubernetes, we are mostly interested in control plane. We don't really care what happens on the nodes locally. Obviously, we are interested in all the interaction between nodes and masters. So, for example, all the requests that kubelet sends to Kube API server, or all the watches that kubeproxy opens to go Kube API server, etc., etc. But we don't really care whether IP tables was written or not on the node, or whether a certain container was run or not on the node. And that's what basically KubeMark does. So in KubeMark is based on the concept of hollow node. Hollow node is a set of 3 containers: hollow kubelet, hollow kubeproxy, and hollow node problem detector. And as you can imagine, I will explain using kubelet. So hollow kubelet is a regular kubelet, but it has some parts mocked. So for example, there is no container runtime interface. Instead, there is a mock which just pretends that container was run. Similarly for kubeproxy, we have mocked all the logic for writing IP tables because we don't really care about it. And all these hollow nodes, they connect to a real master called KubeMark master, and together it forms a KubeMark cluster. And using this approach, we are making basically our tests about 10 times cheaper, which is a really great result. And interesting one note here, Inception-like thing. So as you can imagine, to run, for example, a 5,000 node KubeMark cluster, you need to run a lot of containers. In this case, it will be about 15,000 containers. So how do we do that, right? If we only had a tool that would allow us to run a lot of containers, and obviously we have such tool, it's called Kubernetes. So every time there is a KubeMark cluster, in fact, there are 2 clusters. We have some real Kubernetes cluster where all the hollow nodes are run, and then all these hollow nodes connect to KubeMark master. And this together forms a KubeMark cluster. All right, and I already mentioned observability and debuggability. So either cluster loader or other tools they provided. For example, cluster loader provides features like profile gathering from important Kubernetes components like API server, etcd, kube controller manager, We have built-in Prometheus integration, so cluster loader is able to set up a Prometheus stack inside a cluster that is under test, and then monitors basically everything it's possible to monitor. And then we have these pre-configured Grafana dashboards with a lot of interesting and very useful graphs related to scalability and performance, very useful for debugging scalability regressions. And we also have PerfDash, which basically reads data from periodic tests, parses them, and then display graphs of how a certain metric changed over time over different runs. And this is also very useful to like pinpointing a place where something got broken. For example, PerfDash can create a graph, can show a graph of memory usage of API server, and we can see that, okay, starting from here, it doubled. So most likely here something changed, and it's the place where we start looking for regressions. All right, so on top of this scalability infrastructure, we own a lot of scalability tests using this infrastructure. And again, we could like spend at least 20 minutes describing all tests that we own. It's a lot of tests. We don't have that much time, so I will keep it short. I think the main two groups of tests are pre-submits and periodic tests. Pre-submits, every time you send a PR against Kubernetes, or Kubernetes perf test, you will see some of the scalability jobs running, basically to make sure this PR doesn't introduce any scalability regression. Obviously, we cannot have all the tests as pre-submits. For example, these large tests are too expensive, too long to be run as pre-submits. So that's why we also need periodic tests. And we have a lot of periodic tests, kinds of tests we have. So we really like, obviously, end-to-end tests, because like end-to-end tests are the best way to actually evaluate performance of such complicated system as Kubernetes. The performance tests are the cluster loader 2 tests, and the correctness tests are the regular Kubernetes end-to-end correctness tests that check whether all like main functionalities work. We just run them at really high scale, for example, 5,000 nodes to see whether to make sure that all features that work on a smaller scale, they also work on a large scales. KubeMark that we already described. Then we have a lot of benchmarks, for example, some scheduler benchmarks where we just set up scheduler, Kube API server, and etcd without creating a real cluster and then just simulating some load, or micro benchmarks where we basically test either some methods or like important pieces of code inside Kubernetes code base. And one of the very important group of tests that we maintain are the scalability release blocking tests. So basically, if the tests are not green, if they don't pass, it means that no new Kubernetes release can be released. And these tests are 105,000 node performance tests and 5,000 node correctness tests. Okay, so now all these tests are created in order to protect Kubernetes from scalability regression. So every time we see that a test failed, most likely, in most cases, it's quite likely that there was a regression introduced, and we start debugging. And a note here that scalability is super sensitive, Kubernetes scalability, and we've seen regressions coming pretty much from everywhere, from operating system changes or some bugs, through Golang changes, for example, in memory allocation or like other core Golang libraries that affected scalability, through obviously code, Kubernetes code, like controllers code, API, machinery, etcd, kubelet, etc., pretty much everywhere. And what happens when we detect a regression? We usually debug it ourselves. Once we know more or less what is going on, we either try to fix also ourselves, or we delegate to relevant SIGs. A few examples of recent regressions to give you some intuition about the scalability regressions that we are facing. So we had like two really large Golang regressions in 1.13. That was changes to memory allocation that basically completely broke the scalability of Kubernetes. In Golang 1.14, if I remember correctly, it was some timer changes, so core Golang library, and it also like took us quite a long time working together with Golang team to debug and fix that. Another example is in 1.18 Kubernetes. We realized that cluster started to fail during master rolling upgrade. All right, and protecting from scalability regressions just by looking at the test and reacting to that is kind of a reactive thing. Of course, we want to do more than that. We do more than that. We also try being proactive. And being proactive in SIG Scalability meaning detecting the scalability bottlenecks and then driving improvements to get rid of them. Again, some examples here to give you intuition. Recently we made some changes to watch cache. We added indexes there. We changed the watch cache size to be dynamic. Periodic watch bookmarks, where basically we built on the watch bookmarks API that was added a few releases ago. Changes in node authorizer, basically where we heavily optimize the adding pod or deleting pod paths. Immutable secrets, so a new, much more scalable API for secrets and config maps, and many, many more. Okay, and last but not least, we are also involved in Kubernetes community, consulting, coaching about scalability and performance. One of the most important things here is the scalability approval process. This is part of the production readiness review. So basically starting in 1.19 plus, every KEP will have this mandatory section with questions about scalability and performance. This is to make sure that author of a KEP is aware of potential scalability or performance issues at the design phase. We do a lot of ad hoc scale testing. Example here is parity and fairness. So basically other teams, they work on large changes in Kubernetes, large new features like parity and fairness, and we help them with testing the prototypes to make sure they work as they should in terms of scalability and performance. And also consulting, as I said, being present in discussions about performance, about scalability. An example that I really like, the idea that I really like is consistent reads from cache KEP listed here. All right, and that was pretty much everything. Just one more slide about how to find us. Here are links to our homepage, our Slack channel, our mailing list. We also have these public meetings every second Thursday, bi-weekly meetings. I encourage you to join. And at the bottom of the slide, there are like 2 issue lists that we tag as help wanted. So feel free to check them. If you see anything interesting there, feel free to assign and do it. We will really appreciate. All right, and that was everything. So now it's time for the questions. Thank you. All right, I think we are online. Here's a question. Is KubeMark customizable to mock specific API calls to the control plane? And given that I was presenting, I will let Wojciech, our TL, to answer this one.
So basically, the idea behind kubemark is not really to mock the API calls, but rather mock the underlying behavior of some components. So in particular, like as an example, we are mocking like the calls to container runtime. So instead of like calling Docker to explicitly do something with the containers, like starting them or stopping or whatever, we are replacing that with like a mock implementation of Docker or container runtime interface in general that just claims it does that, but didn't really do anything, didn't really run, didn't really stop anything or anything like that. We are not really mocking the API calls per se. Like we are using the regular API server, like the master part of the control plane. So in particular, API server and etcd that are involved in answering API call or like replying to API call are the regular ones. What you can do is like you can install like your own webhooks as you can do in regular Kubernetes, but it's not really probably what you are asking for. Yeah, I think there's another question. Is it possible to run hollow kubelet without kubemark in a live cluster, for example, in a live cluster? Mateusz, do you want to answer that? Or
yep, why not? So technically it's possible. Hollow kubelet is just a container, so you can run it. You can configure it. Like if you have all the like secrets and keys to connect to your master, then there is like nothing wrong with like it's possible to connect kubelet, hollow kubelet. The question is like, why do you want to do that, right? So that's the question, because as Wojtek said, and as I said, like in hollow kubelet, the container runtime interface is mocked. So basically, hollow kubelet will not run any containers, and the purpose of running hollow kubelet is just to reduce costs of performance tests. But yeah, in general, you can do whatever you want with hollow kubelet.
So I can add one more thing to it. I've seen examples of people doing that actually, and one of the examples is when you generally want to run kubemark, but you also want to run real nodes where you would like real add-ons like DNS or something else that is that is not running on the master, but is running like as a pod in the cluster. So if you want those pods to be really running, they need to be running on, they can't be running on hollow nodes, but you can like mix your cluster with like hollow nodes and those real nodes, and for example, taint the hollow nodes and ensure that real pods will be running only on those real nodes, and all the other like test pods will be can be running anywhere. So yes, in general, there are people that are doing that.
All right, it looks like we don't have any more questions. If there are any questions, will be available on Slack, so feel free to ask the questions there. Yep, and this is it. So thank you everyone for joining us today. Hope to see you around, either on SIG Scalability public meeting or Slack or on some GitHub issues. Thank you.
Yeah, thank you very much.